Great. I also want to, of course, quickly thank again Spectrum for letting us be here. It's an awesome venue. Thanks to Ryan for the live stream, and thanks to all the volunteers for helping us, and of course to all the participants who came, some from very far away to come share their work with us. We're really grateful. So with that, I'd like to introduce Knut Hune and Elektra Wagenad, presenting ISEMS, making solar-powered mesh networks easy. So please welcome them.
Thank you. Thank you very much. Ich denke, ich fange an, oder? So who are we? Of course, you've heard my name. I'm Elektra. I've been working for the Freifunk community since like 2002, 2003. I have been hacking on hardware and software routing algorithms and stuff like that. And Knut?
I'm Knut. When Elektra started working on Freifunk, I was 9 years old, so I didn't work then. I'm a programmer, mostly web, and I joined Freifunk a couple of years ago now.
Next slide, please. So, in Europe or globally, there's something that people call the refugee crisis, and as a part of responding to the refugee crisis, the Freifunk community, our local German-speaking network community, was looking for a solution to bring Freifunk or ping internet access, basic internet access to people in refugees' homes and refugees' camps. And an idea that I had long ago was like to develop a solar controller, so the basic device that controls the charge and discharge of the battery, with an additional feature called maximum power point tracking that I'm going to explain to you later. And so I started developing that hardware in 2017 at the beginning. And the result is what you see here on the left. It's a mobile solar-powered mesh node that can be erected in a few minutes. And on the right side, you see the work of Knut. Maybe you.
Yeah, I'll talk about this later, but basically what we did in the ISEMS project that we're presenting today is making this more accessible by, for example, providing a web app, and that's what you see on the right. So that gives you some stats about the node that you can see on the left, so that you see if your network is performing right or not. So this is an excerpt of a greater picture that shows all the components laid out on a sheet of brown paper. On the right side, you can see the basic HTML information that is presented by a wireless router running OpenWRT with our software. That way you can look at the status of each node in a decentralized way. So even if you're disconnected from the network, by using a web browser, you can check out the local status of your mesh router that is solar powered. So Elektra said that this all started with the refugee crisis, and we just want to provide some use cases for where our system, which is independent solar powered mesh network nodes, would be useful. And one of the examples is urban environments. So sometimes in Berlin, we find people that say, yes, we're willing to let you on a roof and you can set up a node there, which is cool, but then you need to get someone to come up there and drill a hole in the roof so that you can lay a power cable, and sometimes that's more expensive than all of the rest. And by being able to just put the node there, which is completely independent, doesn't need a connection to the outside, that eases setup in urban environments.
So there's also concerns about, is the roof still waterproof after you made that installation? What happens if that installation is hit by a lightning? So for example, we were able to have exposed nodes on some municipality town halls, but the hardware that we installed was a fraction of the cost of the money that we had to spend on professional workers that certify that the roof is still waterproof and stuff like that. So if it's just a solar thing that you can just assemble on the roof without making any holes, that powers itself, so you have no power costs, that simplifies getting access to exposed sites by a great deal.
Of course, there's also other use cases, like if you want to set up an ad hoc installation, and this can be something nice, such as a music festival where you want to provide infrastructure to your listeners, but it can also be something like emergency camp where you want to provide some basic networking infrastructure for the people that live in the camp. And the picture that you saw at the beginning already is for remote areas. So you can imagine a situation like this where there's two communities and they're separated by a mountain or by some obstacle. And the cool thing now is, of course, you could already put a node on the top of the hill, but up until now, you would have needed to run a power cable up the hill, which kind of defeats the purpose. So by being able to properly set up a truly independent node up there, we can probably connect communities that couldn't talk to each other before.
Of course, there have been experiments by people from the Freifunk community for such tasks as well. But for example, we had the situation here in Berlin. Maybe you know the Teufelsberg. There is a Freifunk installation on Teufelsberg, but it was the guys who planned it, they spent way too much money. It's still imperfect. In wintertime, it needs the help of a generator that is gasoline or diesel powered. And so the idea was to design such a system from the ground up, so to avoid all those mistakes that people make. They use a hardware that is drawing too much power, which generates an enormous amount of cost. You need bigger batteries, you need bigger solar panels, and in the end, there's still times where it still doesn't work. Do we have time for the video? Yeah, you can stop the audio. This is like a little video that we made that shows it took a total of 7 minutes to set up the system. Because it's pre-configured, pre-assembled, and yeah, it's intended to be a mobile installation, so it's by no means tamper-proof. So it would be easy to take it away or steal it, but in an emergency situation or in a hacker camp, you can set it up in a few minutes. It erects to about 5 meters of height and has all the bells and whistles that we engineered. Yeah, we skip it.
You can find it on YouTube.
So this is the core component of the hardware. It's an open hardware and open software designed maximum power point tracker. It's built around an Atmel AVR microcontroller with 8-bit and an analog circuitry that is a DC-DC converter, a step-down converter that gives you an energy boost by increasing the efficiency of the combination of a solar module and a battery. The technology is called maximum power point tracking. It's not that I invented it, it's something that already exists. But solar controllers with maximum power point trackers are usually high-priced comparatively to such a small installation. So starting from 120 euros and up, you cannot program it. They're not open hardware, they're not open software. This is the most difficult part for you to understand, probably, but I'll try my best. The red lines is the current of a solar module. We have 2 of them depending on this irradiation strength from the sun. That gray line that goes up there, that is a little bit curved, that's the maximum power point. If you remember some of your physics lessons, power in watts is the multiplication of current, ampere, the symbol is I, and voltage, in physics the symbol for voltage is U. So, for example, if we go to 0.1, that's from a single solar cell. If it operates at 0.1 volt, the current is the same like at 0.3 volt. As you can see from the red line, that is completely straight. But if you multiply 0.1 volt with, let's assume the red line is 1 ampere, we got 0.1 watts. But if the solar cell operates at 0.3 volts and 1 ampere, we get 0.3 watts, which is 3 times the power. There's one point where the voltage already starts to drop a little bit, where you have the maximum coefficient of multiplying voltage and current. And the MPP tracker, it calculates that point and it controls the solar panel in such a way that it operates in the point of maximum power. Okay? Next slide. Here is the result. On the left side, you see the current that is coming in from the panel at 18 volts. And on the right side, you see the current, it's a little bit hard to read. It's 1.59 amperes that is going into the battery. So the current coming from the panel is smaller than the current that goes into the battery. And that boost is achieved because the electronic takes 1.11 ampere at 18 volts and converts it down to 13 point something volts. And that increases the current. And the current is that what charges our battery, essentially. So that's all the components of the hardware laid out on a sheet of paper. Solar module power and so on. I think that's self-explanatory. And this is a self-built node that is running in the trailer park where I live. It's a squat or a trailer community here in the center of Berlin. It's a self-made node. I took a waterproof box. Inside there is a dual band home router that only draws 3 watts. And it's dual band, so dual radio and 2-stream MIMO. And I took one of the antenna ports to connect it to a high gain directional antenna that gives us a strong long distance link. And on the left side there's a little Omni that gives us local access. So that way, that's a way to construct a low power, high distance wireless relay for a community network.
So this is the backside of the solar panel that you can see here, where we also have the OpenMPPT. But the cool thing about the OpenMPPT, which is something that Electra had built already, that we could now build on top, is the fact that now we kind of had a brain in between the router and the battery and the solar panel, so they could communicate with each other and they could give us some information. So you can see the MPPT communicates with the router that is connected to it. That is part of a mesh network which communicates with other routers. And at the end, at one of the nodes, we have a single board computer, such as a Raspberry Pi, that provides this web app that you saw earlier. And I'll talk a little more about that. But essentially, the cool thing that we can see here is that by having this OpenMPPT, which has some kind of firmware that Electra wrote, we can now see information about like what's the battery charge, what's the current temperature of the battery, which allows non-expert users to get a better understanding of how their system is performing, if there's anything that they should be doing.
So basically, the microcontroller is sending some data about the physics of the solar node. And there is a software inside the router that analyzes and prepares the data. We'll see some screenshots of the data right now. For example, we generate a log file that is a CSV file that contains all the useful information. Of course, it's not supposed that you read it on your own. You can if you know the details. Next slide. It also generates a data set in JSON format of the last reading. So if you want to write something on your own using JSON input, you can just download that data. Yeah, illustration of the data fields. We're not going through the details. You can find it on our website. And there's error codes, so a little hex code can give you detailed information about the node. So we tried our best to send the minimum amount of data, because in a mesh network, the amount of data that you consume with your system should be kept to a minimum in order to not affect the performance.
I think this to me was one of the most interesting parts of this project, because as Electra said, she thought hard about how to send the minimum amount of data, coming from a mesh network perspective, that totally makes sense. I come from a front-end development perspective. So I'm used to doing an npm install which downloads 400 megabytes of dependencies, and Electra is thinking about how can we store data in 3 bits or 3 bytes, and how can we squeeze the last bit out there. So this us coming together to see where our worldviews clash, I think that was an interesting experience for the both of us.
So what you see here, that's the Lucy web interface. It's the supposed to be a default web interface in OpenWRT. And the basic HTML page that is generated by the Lua program that I wrote for the routers is in an iframe. So when you open the start page, you immediately get information. And I guess most users would be interested in just seeing the summary. System is fully charged, everything is fine, it's healthy. If there's space available, I also install RRD tool and generate some fancy graphs. So they're decentralized graphs that you can also check on the router. If you have routers with 4 megabytes of flash, that's a tight call. So in a router with 8 megabyte flash, it fits easily, but here it's a little bit tight. That's the setup interface, also in Lucy. We can skip to the next one. And here you can set up power saving modes. There's a script that has several options. So for example, you can just run it at full steam, or you can enable the power save mode that you have in some Wi-Fi drivers. You can stop the secondary radio if it's a 2-radio device and power is sparse. You can stop one of the radios in order to preserve some power. You can have the option that the device enables its radio for 2 minutes, checks if there is any connections coming in. If nothing happens, it goes to sleep for 2 minutes, and it repeats that all the time. It can do the same with hard sleep for 5 minutes, and so on. And more strategies to save power are to come over time. And of course, you can make your own.
So what you just saw is the kind of interface that you get on a single router. But as I said earlier, we have a special router in the system, which is a router that also has one of those small computers like a Raspberry Pi. And what that does is it holds the web app that you saw earlier. So it just contains a JavaScript file and some HTML. And you can connect to the mesh network at some point, connect to this specific router, and you get the more usable interface that gives you an insight of your whole system. So the way that works, you connect with your phone, you get the web app, but of course the router is part of a bigger network. So what the router does, or what the Raspberry Pi does, is it regularly connects to all the other routers. So in our setup right now, every 15 minutes, it just goes to all the other routers and downloads the CSV files that you saw before, stores those in a database, and then also provides web API so that the web app that is now downloaded to the phone can call back to the single board computer and ask it for data, and then get some information about how your overall network is doing. And that looks like this, essentially. When you start the app, you just get a very simple list, which prioritizes the nodes that have that might cause problems. So we see that the first module here didn't send data in 17 days, which is a bad sign. It might also show us something like this node is constantly too hot, or this node is lacking battery capacity. But you can also, of course, click on the individual nodes, which is what you see in the middle screen. And there we provide you some more information about how this individual node is doing. Initially, we showed only the things that go wrong. But again, targeting this to non-expert users, we thought it might also make sense to show all the things that are going right, so that you can kind of exclude things for why your system might not be working. So you might be seeing something isn't working as expected, then you go to this page and you see, okay, apparently everything with the battery is still going fine, so that might not be the cause of my problem. If you're even more advanced, of course, you can click on Show Charts, and you can see the detailed information for the last 24 hours, which also is stored on the router or on the Raspberry Pi. And you can try to visually get an understanding of what exactly is going on in your node there. That's the web app. We initially wanted to demo it. I also made a hosted version of it where one of our Raspberry Pis in the local network just pushes data to a server in the internet. I bought a very cheap server and it sometimes goes offline, but as I learned yesterday, that's a feature that servers sometimes go offline. Yeah, it's a very cheap server. We'll provide that later. There's also a link to it in the slides. But we have some next steps. So one of the things that we thought we might be doing now that we have the Raspberry Pi that collects all the information from all the nodes, we could compare them and we could check things like, okay, we have 5 nodes here and they're all in the same geographic area, but one of them is doing much worse than the other ones. This is something that we could check, and then we could provide the users with information like, maybe there's a branch covering your solar panel, or maybe there's another reason why one of these installations is doing so much worse than the others. Or, of course, you could also compare a single node over time. So you could see the battery capacity is constantly going down here for this single node. So maybe we need to do something there. Of course, we are also looking for more installations. So if this sounds like something that's fun, talk to us. We try to make it as easy as possible to install it, like by providing some setup scripts and providing comprehensive documentation in German only. But if there's international listeners, that's good motivation for us to actually translate it. Yeah.
Well, translating is one of the next steps. I think English is the first language to translate it to. It was we were funded by the German Ministry of Education and Research, so our first priority was to have documentation in German. Well, thank you very much for your attention.
Thank you for the talk. I do have 2 questions. The first one is about the app, so it basically only shows statistics. You cannot manage stuff from out of the web app. And the second one is, so what would happen if we directly connect the battery to this? What would happen if we directly connect the battery to the solar panel without having the MPPT in between? It's still possible, right?
Okay, so far there is no central management in that sense that you can, at a click in your management interface, change all the nodes. You would have to go to the router using the web interface and configure it individually. The second question, if you connect a solar panel directly to a battery, it will overcharge the battery. And if you connect a consumer, it will deep discharge the battery if the power that is produced is not enough. Also the MPPT, so you need to control and stop the charge if the battery is full. You need to control and stop the discharge once the battery is too low. And the MPPT, as I said, it increases the amount of power that you harvest.
Thank you. Thanks for that great presentation. It was fascinating. I noticed in one of your slides there was a line there that said time to reboot. And I was wondering, is there a need to reboot the system every so often, and if so, why? What was that about?
Well, I run nodes myself, and sometimes they just hang. So they might respond to ping, but you cannot log in. They would just remain in that status forever. There is like there's some software like software watchdogs and so on, but it doesn't give you the full certainty that if it is on a remote site where you have to climb a mountain in the Himalayan, for example, so you take 5 days to get to that station, it's better to have a time where it hard resets. And you can configure that. So there's a simple serial command that you can set up the parameters of the microcontroller. So that will give you a hard reboot. I saw you first.
Hi, thanks. That was fascinating. I was wondering if you could say why you also include radio alongside. You said there's 2 radio as well. And what's if this is about mesh networks, can you talk about what's the role of radio in that?
Well, a mesh network, sorry we didn't go into that, but that's out of the scope of this talk in a way. A mesh network is based on multi-point to multi-point capability of radio, or the Wi-Fi protocol as such. If you have a chain of mesh nodes that forward data to a remote node, if you only have a single radio, the bandwidth is cut in half for every intermediate step. So it's favorable if you have a device with multiple radios. So a data packet can come in on one radio interface and leave on the other. The routing protocols that we have, they support this, so they will opportunistically switch the channel. So use radio 1 to come in and radio 2 to come out, or vice versa. But of course, if you have several radios, each of them draws power. There's usually a main radio that it doesn't make much sense to stop that. And there you might have a secondary radio, and it just enables you to stop that. So you have a basic service if you run out of power, or power is scarce, and you have full service. Okay?
Have you thought about adding a third radio, the traffic of that to that 900 megahertz frequency, and you can also like do reboot and that sort of stuff?
I'm part of the LibreMesh project that is striving for creating an open hardware wireless router that you could have the option to add this. And of course, it was by no means my intention to limit the amount of radios. So if you have 3, 4, 5 radios, the script will simply disable all the radios except one. So if you have like multiple radios, they would be skipped. There's one priority radio that will be on all the time. You could make that the radio that is long distance, as you suggested, if you add it to the device. But usually, because it's already networked by wireless radio, it's a matter of, it's a question whether it's useful to have a long distance radio in addition to it. Okay.
I just had a question on a few questions. One on price, the second on the distance of the directional antenna, and the price of the whole thing. Yeah, and then the distance that's covered by the directional antenna, and then how many people are served by the local antenna.
The community has 20 people. The price of such a solar-powered system in general, for the most basic system without directional antennas, is about 200 euros in Germany. That's the price for the hardware you have to spend on building it. The directional antenna, that was an old one that we reused. If you purchase them new, they cost like 50 euros. And the range, it depends on the circumstances. Actually, with that antenna, we were actually communicating through trees on 5 gigahertz. So we needed that massive gain to actually go through the trees. So, but if you have an undisturbed Fresnel zone and you're high enough to deal with the curvature of the Earth, then you can communicate over 30 kilometers or more. But this was just used for 1 kilometer. But with obstacles. Time is up? Yes.